So anybody who's not here, we'll just have to beg you guys for the answers. No, it's okay. I think everybody's here. Probably everybody's here. Okay. Any questions about that? So again, if you came in late, you can keep working on the homework till Sunday. This is certainly one of the harder problems, in my opinion, from the assignment. You do have to do the second case, but I promise that case is very easy. So that should not take you too much longer. Okay, great. So that's the homework. I don't have any other announcements. Really, we're just kind of in the rhythm here. 2 more weeks after today to get us to spring break. So we don't have another midterm till 2 or 3 weeks after spring break. Quite a bit of time. So I think it should be pretty chill. What I've got on the board here on the left side is my usual summary of where we had left off on Tuesday. We had started talking about this idea of the order of an element. And we just have to make sure it makes sense to talk about that. Remember that n is just a positive integer. A can be any integer. But the key thing is that the a and the n will need to be relatively prime for us to even have this conversation. So assuming that the GCD of a and n is 1, the order of a in mod n, and remember this is not a notation in the book, this is my notation. The order of a in mod n is simply the smallest positive integer such that a to the k is back to congruent to 1 mod n. Right, so it's the smallest positive integer that accomplishes that. And again, assuming that the GCD of a and n is 1, we do know that there will eventually be some power of a that is congruent to 1 in mod n. Namely, because of Euler's theorem, we do know already that phi of n is a power of a that would be congruent to 1 in mod n. So at the worst case, we would have to take this many powers of a to get congruent to 1 in mod n. Might be able to get away with less powers than that, but this is the maximum value that your order of a could be, right? Okay, so that's the definition of the order. Is everybody good with that? So if you're proving that the order of a in mod n is equal to some value, it's not as easy as you think. So like if I want to prove that the order of 3 in mod 10 is 4, I have to not only prove that 3 to the 4th is congruent to 1, I have to prove that no smaller power of 3 could have been congruent to 1. People often forget this part. People forget this part, and then they're kind of not proving it at all at that point, because you got to prove that you found the smallest power of your number that's congruent to 1 in mod n, smallest positive power. Okay, anyway, by the way, if the order of a is the full phi of n, if it is equal to phi of n, then we call that a primitive root of n. We called a primitive root of n. So we did this one on Tuesday. 3 is a primitive root of 10, right? Because, well, phi of 10 was 4, right? And then if you calculate the powers of 3, the first positive power of 3 that is congruent to 1 in mod 10 is 4. We don't get back to 1 any sooner than that. So these are a couple of important definitions in this theory of indices, and we're going to talk about index today a little bit, indices and order. Are there questions about that recap at all? Okay. Let's just do one more example here. I just ran out of time on Tuesday. I would have liked to have done one more example. Let's take this one. Let's take n to be 15 this time. Just throw my power up a little bit here. Let's suppose that n is 15. And I would like to find a primitive root of 15. And you can see from the definition of primitive root that you need to know what phi of n is right away. So in order to do this, I would have to look at phi of 15. So I just at least know what order I have to end up with here. So phi of 15, as we know, we can break this into relatively prime factors. It would be phi of 3 times phi of 5. And this becomes just, because these are primes, their phi values are just 1 less than what they are. 2 times 4, which is 8. So we'd like to know that number ahead of time. And what I'm looking for is I would like to look for an element whose order is 8. So I'm looking for an element such that the first power of it that finally gets back to 1 in mod 15 is the 8th power. And no smaller power gets that done. So, by the way, you probably already know that 1, the number 1, and by the way, I'm only going to be looking at the numbers that are relatively prime to 15. So I'm going to look at 1 and 2 and 4 and 7 and those kind of numbers, right? But you probably already have a pretty good idea that 1 is like never a primitive root because you're already back to 1 when you take even the first power of 15. So that the order of 1 is 1. Okay, that's always true. Doesn't matter what n is. So you can go to the next number and try it. You could try 2. You can ask yourself, well, what's the order of 2? Well, I start taking powers of 2. You're looking for the smallest power of 2 that is congruent to 1 in mod 15. Well, 2 squared, 2 cubed. 2 to the 4th. That's 16, right? So 2 to the 4th, that's back to 1 in mod 15. And that tells me that 2 is not a primitive root. Because remember, to be a primitive root, the order would need to have been 8. I should not be getting back to 1 until the 8th power of that number. Okay, well, let's just keep going. What are some other? I said that 4 was another choice. But you can see that doesn't work either, right? Because 4 squared is already back to 1 in mod 15. So the order of 4 is even smaller. We have to skip over 5. We have to skip over 6. Anything that is having factors of 3 and 5 in it can't be considered. Let's go to 7. In mod 15, let's see. So 7 squared is 49. Well, that's not 1. So in fact, what you should do is reduce this mod 15 as you go. So 7 squared being 49 is really the same as 4. And then I know that with 4, I'm going to need 2 more powers. So at best, at worst, it would take 4 powers of 7 to get back to 1. And that is actually true. You can't get there any sooner. So that's not a primitive root. And so I have bad news for you. Because if you try 8, I would like to point out that 8 is the same as negative 7. And so if 7 to the 4th was 1, then 8 to the 4th is really just negative 7 to the 4th. And that minus sign evaporates when you take an even power. So this is already back to 1 as well. I have to skip 9. I have to skip 10. I can go up to 11 because I have bad news for you. 11 is the same as negative 4. And already the squared power of negative 4 was back to 1. So this is not going to cut it either. 11 doesn't work. Let's see. I have to skip over 12. I can go to 13. But 13 is the same as negative 2. So the 4th power of 13 is obviously also back to 1. And then the last number that you could look at would be 14. But 14 is just negative 1. And of course, the order of that is only going to be 2 because it's negative 1 squared, which is 1 in mod 15. Guys, there's some real value in using negative equivalents in this theory. In fact, once you kind of hit the halfway mark of checking these various numbers for to see if they're primitive roots, this second half over here is just like a mirror of the first half. Okay, so whatever powers you had calculated here are being reversed over here. Guys, the conclusion is that this is not possible. It is not possible. The number 15 does not have any primitive roots. And yet this is an extremely important theoretical tool. This is going to give me immediately a bit of anxiety about the following question. Actually, I'm going to make 2 questions here. The first one is, which n's have primitive roots? Obviously, 10 has one, but 15 didn't. So that's a good question. First question is, which n have primitive roots? Primitive roots. That's a very good question. We will have a theorem for that soon. And then the second question is, If n has a primitive root, so such as 10 is an example. If n has a primitive root, question might be how many primitive roots does it have? How many does it have? Another really interesting question that we can ask. And both of these questions have answers that we can write down. Yeah.
Is it a coincidence that all the exponents for those roots are the same as b of the prime factorization of 15?
The 2's and the 4's. Well, you might notice that these powers, they are all divisors of 8, right? That is not a coincidence. In fact, I should just hand you my notes because the very next thing I'm going to say is a theorem about that. Yeah, it's like we didn't really need, like over here, we didn't really need to calculate 3 to the first, 3 to the second, and 3 to the third. It turns out that there's only some of these powers that are even in the running for being potentially getting us back to 1. So that is a good point. Thank you for noticing that. And I'm going to write a theorem down about that. Yeah, to answer these 2 questions, we really should spend a few minutes just getting some properties of order of elements written down first, and then that'll help us to answer these questions. By the way, I may not get both of them answered today. We're probably going to answer the second one today. I don't know about the first. I have to give you a reason to come back next week. So I'll probably keep you in suspense for a few days because it just takes a little while to get to this. So to answer these questions, we need to develop some more facts. So, we need some facts about order. This is all having to do with the order of an element. That's sort of the genesis of the whole topic here. So let's start off with the theorem that Anthony has already kind of hinted at, and it's theorem 8.1. We are in chapter 8, by the way. And this just says, suppose that the order in mod n of A is some number k. So assume that the order is k. Then what this theorem is going to do is it's going to tell us which powers of A would be congruent to 1 in mod n. We know that the kth power would, but there's other powers as well. So in particular, A to the h will be congruent to 1 in mod n. Make sure your h's don't look like n's. I'm using the same notation as the book, but sometimes I see people writing h's that look just like n's, and it can be very confusing. So which powers of A are congruent to 1 in mod n? The answer is any power that is a multiple of k. So h has to be a multiple of k. In other words, k has to divide h. Okay. So if if 3 to the 4th is congruent to 1 in mod 10, then so is 3 to the 8th, 3 to the 12th, 3 to the 16th, and so on. It's probably not hard to believe that, and the proof is very short. I will write down the proof, but this is not any kind of a bizarre result that you would probably expect this, right? But you won't get any other powers of A being congruent to 1 other than multiples of the order. Yeah, so that's the idea. Okay, so in other words, okay, so let me just make sure that it's clear. If I already know that the 4th power by Euler's theorem, if I already know that the 4th power of 3 is going to be congruent to 1, right? The order of A, the order of 3 could be less than 4, but it would have to be a divisor of 4. Because this tells me right here, I already know that the 4th power of 3 is going to be 1. And so this is my h. The 4 is like my h in this theorem. So the actual order of 3 is a divisor of 4. I didn't need to check 3 cubed. 3 does not divide 4. So I could have just skipped that one. See what I'm saying? I'm kind of reverse engineering the theorem. I'm saying, oh, I don't know what the order is yet, but I find some power of A that's congruent to 1. Well, then I know my order can't be any old number that's less. I know the order is less than or equal to phi of n, but now it has to actually be a divisor of phi of n. It has to be a divisor of phi of n. So that's kind of how you can use this theorem. You guys with me? Okay. Looks like the heat is getting to you guys. Some of you look a little bit worn out from the weather, probably, or maybe it's just I'm stealing all the energy from the room. That sometimes happens too. Let me write down the proof of this one. Stay hydrated. That's good. Yeah, so I'm going to prove this forwards and backwards. Let's go backwards a little bit here. Let's assume. I mean, this is really, really straightforward. Let's assume that K divides H. And then all I'm going to do, guys, is I'm just going to look at A to the H. And of course, that will be congruent to A to the, I'm going to call it KQ. And Q, of course, is, I should have written this here. So basically, K times Q is equal to H. This is some integer Q. I should have inserted that into the proof. So you're just dividing K by H, and you get a quotient of Q. Divide, H by K, I should say. I get a quotient of Q. So you just put that in, and the order of A is equal to K. Well, that means that, so let's just put some parentheses around this to really emphasize it. I already know that A to the K is 1 in mod n. So there's your proof. It's a one-liner. It's a one-liner. The backwards proof is a one-liner. It's just that short. Okay. Let's prove the forward direction also. But before I do that, let me make sure I'm not going too fast. Is everybody with me? Okay, I just want to prove that A to the H is congruent to 1, but if it's a power of K, then, or if it's a multiple of K, then you can just replace this H with K times something and just factor it out. It's real straightforward. Okay, the forwards direction, I would assume that A to the H is congruent to 1 in mod n. And what I'm going to do is, this is a powerful strategy, and we've seen it before, for showing that one number divides another. I'm just going to use the division algorithm and try to convince myself that the remainder of that division algorithm calculation is 0. There is no remainder, which would mean that the K does divide H. So by the division algorithm, this is slightly longer, guys, but it's still a very short argument. By the division algorithm, I'm going to write H as K times Q plus R, my usual expression of my integer. This is for some integers Q and R is between 0 and n minus 1. So my remainder should always be less than n. Okay. So far, so good. Now, so that means, so we already have a 1, which is what A to the H is. I'm just recopying the assumption here. I'm going to replace the H now with K, Q plus R. This is all going to be in mod n. It's all going to be in mod n. And now I'm just going to use my rules of exponents here. This is A to the K to the Q times A to the R. So this is the algebra step. But A to the K is 1 because the order of A is K. So that just means that this is just A to the R. So the A to the Q part, the A to the H K part becomes 1 in mod n. Everybody got that? Oh, what do we have now? We have a power of A that has been reduced to 1 already, but that power is less than, Yeah, I have a typo here. You see the typo? I was dividing h by k. So my remainder should have been less than k. This should not have been an n minus 1. It should have been a k minus 1. I'm so sorry. Getting my alphabet soup screwed up. Maybe the heat's getting to me. That should have been a k. Yeah, so k minus 1 here. I have found a power of a that is congruent to 1 in mod n, but it's too small. Because remember that the order of a was k, and that's the minimum positive exponent. That's the minimum power of a that gets you back to 1. So the only conclusion you could draw is that this r must be 0. Now, 0 is not in the natural number set. So the only way to sort of avoid a contradiction right now is to conclude that the r is 0. If r is bigger than 0, then you really have a bad contradiction because you found a smaller positive power of a is congruent to 1. Right. So r is equal to 0 by the definition of order. And so if r is equal to 0, that just means that h is equal to kq. And that just means that k divides h, which is what we are trying to prove. Yeah, so that's how that should work. Sorry about that. I hope everybody fixed that. This was a k minus 1 there. Yeah, okay. Does that make sense? Pretty straightforward. Back when I was a kid, and I mean really a kid, like two or 3 or 4 years old, my parents tell me, I don't remember this, but my parents tell me that I loved calendars and I loved clocks. And so as a kid, I would make these things. I remember I would make these calendars for Christmas and pass them out to my relatives and whatnot. Same thing with clocks. I was really big into clocks. So of course I have a clock way of thinking about this. This is just modular arithmetic, but it's really in mod k that I want to think about this. So if I'm going to just draw a little picture for you. There's 1, and then here's a. I'm going around my clock right now. A squared, a cubed, a to the 4th, and we go dot, 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 dot. And then eventually we get over here to a to the, it would be k minus 1. K is the order of a. And then this one then becomes a to the k again. So it's like just like the way your clock works, and then you can wrap around the clock again as many times as you want, right? So these are all the different powers of a, and you finally get back to 1 for the first time at the kth power of a. Yeah. So that's kind of a good way to think about the order concept. It's sort of the smallest clock you could make. It's the tightest wheel that you could make there. Also, just as a quick remark here, I think I'll put this one right here, and then we'll state another theorem that I think this clock probably motivates for us. The theorem is just that, or the remark is just that the order in mod n of a has to actually divide phi of n. And that's just immediate from this box. Because we already know that by Euler's theorem, a to the phi of n is congruent to 1 in mod n. And that just means that phi of n should be a multiple of whatever that order is. So whatever the order of a is, that's the first time you get back to 1 on this clock. The phi of n could be several more times wrapped around. But it's going to be a multiple of the order. Yeah. So I think this should make the next theorem seem pretty clear. And I'm going to write it down here. This next theorem really illustrates why when you're writing congruences, you always need to write down the mod that you're working in, because this theorem has 2 different mods going on. So here it is. It's theorem 8.2. And this just says, again, suppose that the order in mod n of a is equal to k. It's exactly the same assumption that we had on the first theorem. And what this is going to say is then a to the power of I is congruent to A to the power of J mod N. So when are two powers of A basically the same in mod N? So you kind of look at this clock idea, right? And the thing is that this clock has only K different, directions, right? K different directions that goes around the wheel there. So this is if and only if. I bet you can fill it in. I should be congruent to J, but in mod K instead, right? This is a wheel of mod K spokes, I guess you can call it. So the mod changes. I think we had a homework problem a while back where I asked you to give a counterexample that just because A to the I is congruent to A to the J in mod N doesn't mean that I is congruent to J in mod N. Now we know what it should have said. It should have said that I is congruent to J in mod K. So you just have to change the modulus to whatever that K value is. And yeah, the result I think is fairly clear. And there's a nice corollary from this. I'll write down the corollary as well right here, which is just that, again, if we suppose that the order in mod N of A is equal to K, set it up exactly the same way one more time, then all of these lower powers of A, so that would be A squared, A cubed, and dot, 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 up to A to the K, right? Those are the sort of the first pass around the wheel there. They are all mutually not congruent in mod N. So these are mutually incongruent mod N. If two of them were congruent, then the exponents would have to have been congruent in mod K, but you can see clearly that none, if I take any two of these terms and I compare the exponents, they cannot even be K apart. The farthest apart these exponents could be would be maybe the first power and the kth power. Well, that's not even K, that's K minus 1. So no two of these are going to satisfy this condition here with the exponents. And so that means that no two of those powers of A are congruent to each other. Yeah, no two of those powers are congruent to each other. Okay. Questions so far? So far, so good? By the way, so I would just recommend, I don't think I'm going to do this proof. I might recommend it might be worth trying to write it down. You're going to use the first theorem, of course, to do that. So for the proof here, I will skip this one, just call it an exercise, just for practice. It's not hard. It's not hard.
So the corollary.
The theorem is what I'm talking about. The corollary, I think, is more or less just a statement that's clear. Like this is just following directly from the theorem, but the theorem itself, yeah, the theorem itself is something you could try to write down using theorem 8.1 as a tool. Okay, but I'll leave it at that for now. My next question is, okay, so the order of A is equal to K. What about the order of these other powers of A? Like, because again, we're going to be looking for primitive roots. And so it'd be nice to know the orders of lots of things to see if the order is equal to phi of n. So there is a theorem for this as well, which I will put right here. 8.3, cruising along here, guys. And this is what this says. So again, for the umpteenth time, let's suppose that the order in mod n of A is equal to K. So again, the smallest power of A that is congruent to 1 in mod n is the kth power. Okay, let's assume that. Then let's let H be some number greater than 0. So let's let's just let h be in the z plus positive integer. Then the order in mod n of a to the h. This is what I want to talk about. What is the order of that? Well, it turns out that the order of this one is you take the k, which was the order of the original a, and actually the order is going to come down. That makes sense because after all, if you're taking powers of a, to begin with, you would need less powers of a to get you back to 1 than if you, you would need less powers of a to the h than you would need powers of a. So like if a to the 12th is 1, well then for a cubed, I would only have to raise that to the 4th power to get back to 1. So you can get away with something smaller. What needs to go on the bottom? Does anybody have a guess? The GCD of K and H is exactly right. That's excellent intuition and is exactly correct. Yeah. Of course, this is an integer value because the denominator does divide into K. So let's prove this one. The intuition may have been good, but the proof sure isn't. It's not terribly intuitive. There's a lot of notation for this, so bear with me. But let's see if we can do it. I think we can do it. So for the proof of this theorem here, so I will set up some notation here. I'm going to let D be the greatest common divisor of K and H. Use that notation. And so, of course, D divides both K and H. So I'm going to write H as DH1, and I'm going to write K as DK1. And this is for some H1 and K1 in the integers. And we can note while we're at it that H1 and K1 have no common factors, because if there was common factors between the H1 and the K1, your GCD would have been bigger than D. So D is supposed to be the greatest common divisor. So there better not be any more factors inside of the H1 or the K1. There's no common factors there. Yeah, so that seems pretty reasonable. Now I'm trying to come up with a formula for the order of A to the H. Let's give that a name. I'm going to call it R. So let's let R be equal to the order in mod n of A to the H. And what the claim is that R, which is what's on the left side of the formula, should be equal to, what is this? This is K over D. If you look at the notation, K over D is actually what I'm calling K1. If I can prove that claim, I am good to go, right? Because if I prove this claim, then that would prove that the order of A to the H is equal to K over D. This is what the theorem says. And I'm going to prove this claim by proving two things. I'm going to hopefully convince you that R divides K1, and then I'm hopefully also going to convince you that K1 divides R. If I can prove both of those two things, I think you're going to be convinced that R is equal to K1. You guys don't look too convincible. I don't know. Sort of a low energy day. Didn't you guys go to the Pi Day thing at noon? Like I was there and I had so much sugar, I could probably run around up here for the next 4 hours. It's not Pi Day, it's approximation to Pi Day. And what I loved about it, I got a nice jab in. So the person running it, the faculty person running it is an applied mathematician who's really good at approximation theory. And I said to her, well, gosh, today is 3.12. You could have waited till tomorrow. You would have had a much better approximation. This does not bode well for your career. But yeah, so they, I think they figured nobody's coming on Friday, so that's why they did it, but I was perfectly happy to have pi on any day. You could approximate 3.14 by any number and I'll probably still show up. Any date could be an acceptable approximation in my book. In theory, you could have approximation to pi day every day of the year. And nobody could argue it. Yeah, it's an approximation. Might not be a good one, but it's an approximation. Anyway, so yeah, if it seems like I have more energy than everybody else in the room today, that's probably why I had pi. All right, let's see if I can convince you of these two statements here. Okay, that R divides K1 and that K1 divides R. Well, by definition, so let's just note here that if we take A to the H and we raise it to the K1 power, this is the same thing as A to the, I'm going to replace my H with DH1. So the H is the same as DH1. So this is where you have to follow the alphabet soup a little bit. But DK1 can be recombined as K. So this becomes A to the K H1. And what is A to the power of K going to be in mod N? 1, right? It's 1 because the order of A was K. That means when you take A to the K's power, you get 1. So this is congruent to 1 to the H1, which is really just 1. And that would be in mod N. Oh, so I found a power of A to the H, which gets me back to 1. The smallest power of A to the H that gets me back to 1 is what I'm calling R. And any other power of A to the H that gets me back to 1 has to be a multiple of that one by the theorem 8.2, theorem 8.1. Right. So therefore, thus R divides K1. Right. And that, yeah, that is by theorem 8.1. So as soon as you know what the order of your element is, the only powers of that element that can be congruent to 1 are the multiples of that order. So this order was called R. And so any other power of A to the H, including the K1 power, any other power of A to the H that gets me back to 1 has to have been something that was a multiple of the smallest power of A to the H that got me back to 1. Clear enough? That's this part. That's this part. So the R divides K1, and now I just have to convince you the other way around that K1 will also divide R. So let's get into that. So also, let's just take a note. If we take A to the HR, okay, so I'm just pulling this kind of out of a hat for a moment, but A to the HR is, you know, A to the H to the R. And again, we are assuming that R is the order of A to the H. What's that mean? That means this is the smallest power of A to the H that gets me back to 1. So it does get me back to 1 in mod N. Let's see. Oh, so I found a power of A that's back to 1. That power must be a multiple of the smallest power of A that gets me back to 1. So this means, again, by theorem 8.1 again, K would divide HR. Keep in mind what I'm trying to prove. I'm trying to prove that K1 divides R. But if K divides HR, let's plug in. K was DK1 and H was DH1. Just sub that in there. get rid of the D's. Get rid of the D's, and you've got K1 is dividing H1R. But here's where we use this assumption that H1 and K1 have no common factors in them. So you probably remember that, okay, well, if K1 doesn't divide with any common factors, has no common factors with H1, it must divide fully into R. That was Euclid's lemma, right? So the last line here, by the Euclid's lemma, we get that K1 actually has to fully divide into R. And that's the other half of this two-part purification here. That proves our claim. And our claim is literally what this statement is, just with some letters substituted in to make it kind of nice in terms of writing it down simply. Okay. Are we okay with this then? Look okay? So you can see that there will be other powers of A that will have the same order as A itself does. As long as this denominator is 1, your A to the H should have the same order as A itself did. Let's just write that down. That's just kind of a special case. I'll just call this a remark. Again, this really doesn't need a proof. I will just put this here as a remark. If the GCD of of H and K, or I'll say K and H, if that is 1, then the order of A to the H in mod n, ord sub n, is equal to the order in mod n of A itself. So that's an interesting remark. Actually, this is sort of starting to speak to that second question. Remember what the second question was? I had the two questions. The second question was, if n has a primitive root, how many primitive roots does it have? Well, if you can find one primitive root, let's say it's A, then you're going to have other elements that also have that same order that's required to be a primitive root. So there might be other, so as soon as you have one primitive root, you'll be able to create some others. That's really what this is saying. Yeah. Let's do another example with maybe pick a different number here to play with. And I want to see if we can identify some primitive roots. Really, the primitive root is this powerful tool that we're getting to, but I had to prove these first, whatever it is, 3 theorems about order to just kind of set the stage for it. And I think at this point I can just do an example. Let's take n to be 17. By the way, guys, put these notes somewhere where you're not going to lose them, this example, because next week I'm going to want to come back and revisit what I'm about to show you here. So this is kind of an important example for the purposes of what I'm going to do. I'm going to make a big table here, guys, although it only has 2 rows. A 2-row table. And in the first row, I'm just going to put my A. And in the second row, I'm going to put the order in mod 17 of A. Now, the only numbers that even have an order are the ones that are relatively prime to 17. But fortunately, 17 is prime already. So every number from 1 through 16 is going to have an order. I want to actually, I hope you've left enough room for 16 more columns here. Might have to turn your paper sideways. So we'll just label all of these numbers here. Just enough room. I'd like to try to find the order. Now remember that phi of n in this case would be 16. And remember that the order of any number has to divide phi of n. It's not just less than or equal to phi. If we started the day saying, oh yeah, the order of everything is less than or equal to phi of n. But then we proved theorem 8.1. which basically says, and the sort of the corollary of it, which basically says that the order of an element must divide 16. Why is that again? Well, it's because I already know that for every one of these A's on the board, I already know this is true. So what's the order of A? Well, it's the smallest power of A that gets me back to 1. And this 16 has to be a multiple of that smallest power. So what numbers could be that smallest power? Well, 1 or 2 or 4 or 8 or maybe even 16. Yeah. So everything that you're going to see me write down on the second row is either going to be a 1, a 2, a 4, an 8, or a 16. It has to be something that divides 16. Now, the order of 1, as we said earlier today, is just 1. That's kind of a no-brainer. And while I'm at it, let's go to the other end. 16 is the same as -1. The order of -1 is always 2. I guess unless you're in mod 2, in which case the order of -1 is just 1. But for the most part, those are sort of the two easiest numbers to fill in. Okay, let's think about 2. I want to figure out the order of 2. So I start taking powers of 2 until I get back to 1. So I start with 2, that's not 1. 2 squared is not 1. 2 cubed is, don't have to do it. Remember, the order has to be a divisor of 16. So I can basically, this is 4, and then I can just square that. I can just power myself up quickly. So I can go up to 2 to the 4th. All right, well, that's 16. That's not 1. That's not 1, but I can see that it is -1. 16 is -1. So I already know now that 2 to the 8th is going to be 1. So the order here, the smallest power of 2 that gets me back to 1 is the 8th power of 2. You don't have to wonder, well, I wonder if the order should have been 5 or 7 or 3. No, it can't be any of those. It has to be a divisor of 16, and there's only a few of those to look at. Okay, so the order of 2 is 8. What about the order of 3? So I can go 3 to the 1st. Nope, that's not it. 3 squared, that's 9. That's not it. We're working in mod 17. I'm going to skip the 3rd power. So this is 9. I'm going to skip to the 4th power of 3, which is really just 9 squared. 9 squared is 81. How does that jive with 17? I don't think it's 1, right? That's not congruent to 1. What is it congruent to? I think it's 13. Yeah, so I think I got that right. So yeah, because 68 is a multiple of 17, and so 13 would be, if I add 13 to 68, I do get 81. However, I don't really like using 13. I would rather use a better number, which would be what? -4. Yeah, make it a -4. Great. Okay. Let's power it up again. Let's square it again. 3 to the 8th. 3 to the 8th would be -4 squared. Well, that would be 16. But 16 is still not 1. So you know what I'm going to conclude right now? That it has to be that the order is 16. It can't be more than that. And we've checked 1, 2, 4. We've checked the 1st, 2nd, 4th, and 8th powers, and we did not get 1. So it must be the 16th power. Yeah, so that's a 16. If we go to 4, so now you want to try to start taking advantage of some of the work you've already done. If I want to know what the order of 4 is, I have to realize that 4 is really 2 squared. And the order of 2 was 8. So that would mean that, 4 to the 4th is, 2 squared to the 4th. Well, that's already 2 to the 8th, which was 1. So the order of 4 is only 4. Yeah, so I'll put a 4 here. Okay, and by the way, these are all even powers of these numbers, right? So like, for example, 15. 15 is the same as -2. So if 2 to the 8th was 1, -2 to the 8th was 1. So you can start filling this in kind of from from both ends, right? You can fill it in from left to right, but at the same time, it's coming in from right to left. Those numbers have to match. Because all you're looking at here is a minus sign. That's not for every case. That's partially because I'm using a power of 2 for my phi of n. So all of these numbers are even powers, so the minus signs don't matter. So you have to be a little careful in general, but at least in this case, we can get away with that. Maybe I will fill in the rest of it for you and let you take my word for it. The order of 5 is also 16, and so is 6, and so is 7. Those are all 16s. And so that means coming from the other direction, 12, 11, and 10 will all have order of 16 as well. And then in the middle, both 8 and 9 have an order of just 8. So that is the entire table. And you see, I assume you see the primitive roots there. The primitive roots are any of the elements that have order of phi of n, which is 16. And so we have primitive roots, which are 3, 5, 6, 7, 10, 11, 12, and 14. There are actually 8 of them there. There are 8 different primitive roots. Okay. So what I got to try to do in 5 minutes is get to the answer to the second question of how many primitive roots you will have. I can state the big theorem here, and then the corollary will be the answer to the question. So let me state the theorem first, and then we'll kind of go from there. Everybody okay with this? Any questions on how that works? Okay, so let's state one more theorem for today. I know I've kind of been going heavy with you guys on some theoretical stuff here, but nice to make some good progress on this. So theorem 8.4. As usual, we're going to let the GCD of A with n be equal to 1, like always. And then I'm going to let A1, comma, A2, comma, dot, 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 comma, A sub phi of n be the numbers relatively prime to n. And when I say that, I mean those are the numbers relatively prime, sort of between 1 and n. So the a sub i's are just the values that are between 1 and n that are relatively prime to n. Remember, what is the definition of phi of n? It's the number of integers between 1 and n that are relatively prime to n. So I'm just saying, let's suppose we list them all down. Right. So then if A, they shouldn't be using A there, but they must use an A there. I would rather call this R, but that's okay. I'll use an A. If A is a primitive root of n, if we have a primitive root of n, that would just be an element whose order is phi of n. Then I'm going to put an asterisk here, guys, because this is the key thing that I'm going to write down. If I look at A and then A squared and then A cubed, and I go dot, 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 all the way up to A to the power of phi of n. Notice I have just as many numbers here as I have listed up here, right? And also, these are all going to be relatively prime to n as well. If A has no common factors with n, then neither does A squared or A cubed or A to the 4. You're just repeating the same factors, right? So these are all relatively prime to n, and even more than that, no 2 of these are congruent to each other. Why not? Because I haven't even made it around the clock one time yet, right? The first time I get around that clock is the phi of n time, because we're talking about a primitive root, right? The order of A is phi of n. I'm not duplicating. No 2 of these could be congruent in mod n. This is kind of that theorem 8.2. So what does that tell you? that tells you that this list of phi of n numbers must be the same as this list of phi of n numbers, just potentially in a different order. That's exactly what this theorem says. These are congruent. These are congruent in mod n to A1, comma, A2, comma, dot, 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 comma, A of phi of n in some order. In some order, that's the point. Right, in some order, those are going to be the same elements. That's what the theorem says in this case. And yeah, so what did I write for a proof of this? My proof, I will write down the proof now. It's basically what I just said out loud. It's one sentence. It's a one sentence proof. None of the numbers in the star, the asterisk line there, those powers of A, none of those numbers can be congruent, and this would be in mod n, to each other by theorem 8.2. That's the one that just says that two powers of A are congruent to each other if and only if the powers are congruent modulo K. But in this case, the K is phi of n. And these are all different powers of A that are no more than, they're too tight. They're within this phi of n interval. So that's it. But they are all relatively prime to n. So that's the proof. So now I have to write down the corollary. I'm out of time. Darn it. So bad at this. It's okay. I'll give you a reason to come back. I'm actually going to give you the answer to how many primitive roots an element has. Basically, what we're going to say is that if A is a primitive root, then some of these will also be primitive roots. Which ones? They'll be the ones such that the exponent is going to make the order of A to that exponent still equal to phi of n. So just real quick, the order of A to the H, right? It's basically whatever the order of A was, this was our theorem just a minute ago, divided by the GCD of the order of A with H. Yeah, and so I'm thinking of my primitive root, the order of A is phi of n. So the numerator is phi of n. The denominator is phi of n, GCD of phi of n with H. So it's just how many H's are relatively prime to phi of n. That is better known as phi of n. Let's write it down. I'll come back on Tuesday and re-explain it because I know I'm out of time. If n has a primitive root, I gotta get you to come back. I'll use that as my excuse to stop. If n has a primitive root, it has exactly phi of n. Get that right. Phi of n of them. What is phi of 17? Let's see, that's phi of 16, and phi of 16 would be 2 to the 4th minus 2 to the 3rd is basically 16 minus 8, which is 8. 1, 2, 3, 4, 5, 6, 7, 8. Ta-da, proof by example. All right, I'm gonna leave it at that. I will prove this next Tuesday. I'll tease you for 5 days to think about it. It's not very hard to do it, but I need more time to write it down. I don't wanna overstay my welcome here. We'll leave it at that for today, guys. Thanks for a great week. It's been great seeing you again, as always, and I will look forward to the next time. If you need help on the homework, let me know. Let me know. You can turn it in as late as Sunday night. As long as I can get them graded on Monday, I'll be happy. All right. Bye. You're welcome, guys.
Yeah. That was a great display right there.